Hi there, this video is all about creating this kind of cool sort of inky fluid feel using a very cheap filament solution in Houdini. And I'm also taking the chance to guiding you through how to navigate, how to attach data, how to work with objects in the DOP network. So hope you enjoy and let's move on. Alright, so filaments. Let's take a look at filaments and what those are in Houdini. So if we take a look at this slice of a 2D fluid and imagine you have this line running inside all the center of these vortices, what you have is something like this, where you have this circle, right? So this closed line is what Houdini calls a filament. So it's a line that where it's going to sample some forces that can run in a spiral fashion that gives this sort of fake fluid feel to it. Okay, its benefit is that it's much cheaper to simulate, so it's very fast. You can simulate with a lot of particles, and it's nicely controllable. So let's take a look at that in Houdini. As always, I want to start with a clean heap file. So let's create ourselves a geometry container. Let's dive inside. I will also create a circle. Let's rotate that 90 degrees so that faces up, and also let me transform that into a polygon with a few more divisions. Now I want to also run a polypath node so that it extracts only the curves, and I also want to give it a bit more interesting details. So let's add a attribute noise to noise the point positions. So let's set SP, let's set the range to 0 centered, and let's amplitude a bit more, higher element size. Let's also add a bit of animation, and let's increase the pulse duration so it's a bit slower. Let's toggle real time and play, and let's take a look, and it looks good to me. I'm not too much interested in working at the proper scale for this example, so we are basically running a 1 meter radius circle. Cool. Now let's probably start creating our pop network. Before that, I just want a disclaimer here. I want to make this tutorial be a bit more interesting in the way that it's going to make you guys probably know a bit more of what's going on inside a DOP network. Because that's for me in the past it was a struggle to actually exactly know what's happening. We have a lot of different concepts from what I have in SOPs, so probably this is a good chance for me to try and explain a bit of what I know for you. Okay, so yeah, let's create a DOP network, dive inside, and there we go. We want to create first a pop object. Again, I don't like using shelves, so let's just start typing, and a pop solver. So a bit of background on these. If you take a look at your spreadsheet and you go to your object, you can see we have a lot of information here. So basically the way DOP networks works is that it creates a lot of data, and the data lies into folders. So it's a very simple concept. It's like a file system, just like Houdini is. In fact, just you are like working in high-level nodes that will basically transform data and store in different places. So that's all about DOPs. Now we are going to start creating our filament here. So let's source some particles. Let's create a pop source, and what I want to do is use the curve itself. Before creating the points, let's actually transform that so that our fluid can travel along the y-axis. So let's use time, so minus $t times 0.2 maybe, so it's going to travel downwards. Let's do times 2 instead, or is it too fast? Maybe not. Let's go with 0.2. And okay, let's go to the dot network. So in here we can use our, so we're going to scatter onto surfaces, and we want to use our first context geometry. So if we hit play, we have this, which is not much interesting. So first thing I want to do is to try and get rid of those faceted or sliced emissions. So I want to jitter at the birth time. So for that we want to create a, in the birth tab, we want to create a just born group. So that group will only contain particles that like in the first frame of their lives. So let's call that just born, and let's create a pop wrangle that's going to serve as a jitter, or jitter just born. Let's name that properly. Okay, and that's going to only run over the just born group we created. And the expression, so let's go a few frames ahead just so that you can see exactly what we are doing with this. So we want to transform p.y, and let's add to that a random using the id as a seed, and let's also fit that between a variable probably. So let's create a variable first. So float jitter will be a channel of type float. Let's call that also jitter. And what we want to do is fit between minus jitter to jitter, and that's basically it. So let's create our parameters here, and it fits 0, 1 because we're running over a random function. And there you go. Now if we increase the jitter, it's going to start jittering the particles that are born at that frame. So let's do something like this, and let's play that again and see what that gives us. Much better, so we don't see the slices. So let's start with that. Now what I want to do is to start looking at the filaments. So let me just save that so we can keep working on this file. So before everything, filaments need or can have two attributes that you need to store at the primitive level. So I'm going to create those right away with a wrangle, and let's call that set filament attributes. Okay, and those attributes are strength and thickness. Okay, and we are going to use those to control how the particles flow around that filament. So let's create those. Those are all floats, of course. So strength, and let's drive with a channel so that it's easier for us to change. Same for thickness. Let's just copy and paste those names here, and there we go. So let's give it a strength of 5 and a thickness of 0.25 just to start. So let's go back to our dot network and start visualizing that. So what I want to do is to create another pop wrangle, and that's going to call the filament velocity, right? So you could make use of the filament solvers object and sources and pop advect by filaments. Those are all made for you to also work with filaments, but I find it much easier to just work with a simple function that is used inside the pop advect by filaments. If you go dive inside and go into the pop vop, you see it uses a function, or in this case a node, that is called filament sample, and I did try and search inside here. There you go, filament sample. That's the only thing we need actually. So instead of using all those nodes and using a proper like separate object for that, I just want to use a pop wrangle, and that's going to be much easier. Okay, so let's just go directly to our pop wrangle. So one thing we need to change is the inputs. So the input number 1, I need to change that to the incoming filament or the incoming polyline here. So let's change this input 1 to first context geometry, And what I want to set is a attribute on the particles that is going to be called filament val, okay, because that's what filament sample will do for us. So sorry, it's a vector, so vector add filament val will be a filament sample of the geometry 0, which remember, geometry 0 is not the particles themselves, it's actually the curve that is fed into the dot network. And I want to sample that filament velocity from a specific position, which is the second argument, and the position is our point position, and that's basically it. So the filament sample will give us a velocity based on our position and in reference or relative to the incoming filament or the incoming polygon line. That's all that it expects. Okay, so great. Now what I want to do is instead of just pressing play and see that working, I want to actually give you a way or a means to visualize that thing in here, and actually that's a good opportunity for us to see how the dot network works and how the objects and data flows through the dot network. So what I want to do is to actually create a velocity field and actually sample that value and look at that as streamers or as some vectors. So the way we can do that is, first we can add a vector field to this object. So again, remember, a object can hold data, so that's basically all there is to a dot network: objects holding data and solvers. Okay, so this object, so we have a few attributes that lies inside the geometry. So the geometry is a data that is lying inside a pop object. Okay, so if we go to the spreadsheet, we can see pop object, this is an object, then we have a geometry, and that geometry is holding all the values for all attributes for our particles, but we also have other elements in here. So we have colliders, we have physical parameters, we have solvers, we have source objects, we have a lot of stuff in here. So we can also add ourselves. So for example, we can add a container. So a container is another top level object. So if we add that, you see we added a container. We can change the name. Let's call that my container. And there you go. We have a new container. And inside here, we can add a few data or a few elements in there. So you can start understanding how data will work. Okay, so what we need to do now to visualize that filament velocity is to create a velocity field. So we're working with volumes, right? So to create a new field, we can create a vector field. It needs to go under your pop object because objects is what holds all the data. Okay, so it goes under the object, and there you go. We create a new field, vector field. So we can give it like a proper name. So let's call that $OS for operator string, which is the name of the node, so it's more easily visual, you can visualize on the network. So let's call that filament val, and there you go. We have this icon which is for fields, filament val, and we have a lot of initializer, initial information in here which you can change, but just so that you know, if you middle click the object and move one frame so that it starts evaluating the dot network, so you see here we have a field. So I think it only shows in here when you have actual data inside it. So there you go. But you can see on the data tree here, we have the filament velocity field already created, and this is of type a vector field. Okay, cool. So still nothing on the viewport. It's all the same. We haven't changed anything yet. We are storing this filament val at an attribute, and this is actually being stored at the geometry, which is the particles themselves. So you can take a look at that by going to geometry spreadsheet, then pop object 1 geometry, and inside here we probably have a new attribute called filament, And there you go, filament vel, which is a vector, and it's holding all the velocities for all the points at all the time steps. And that is great, but we need to see that on the viewport. So how we can do that? We created our first vector field. Now we need to populate that. And the way we can populate that is by using microsolvers. So microsolvers, there you go. We have one that is called gas particle to field. And before actually assigning values, let's first create a visualization for this node, because by just creating the field, it won't be able to display on viewport. So you actually need a visualizer for this one, and the way we create that is by creating a vector field visualization node, and you need to attach that visualization to your velocity field. So you can see the green ports match here, so you can just connect, and as soon as you do that, if you go to your field, you have a new visualization node, which you can see. Let's uncheck that, and you see we don't have anything. If you connect and go one frame forward, there you go, visualization, and that's that will allow us to see the field values on the viewport. Okay, but still you can't see anything because you need to check show guide geometry, and also I'm going to check the bounding box, and there you go. So this is your field. You don't have any values yet, so what you're seeing is the bounding box of the volume. And if you play, you'll see that it stays static, but what we want to do is to actually see the field growing together with the particles, right? So we need to actually sample the values from the whole bounding box of the particles. So to do that, what I'm going to use is yet another microsolver that is called gas resize field. Okay, so we are going to resize that velocity field we just created following the particles. So the field we are going to resize is filament vel, and the reference could be either another volume or another field, or it can also be geometry. So geometry is the default name for the points themselves, and we are going to use that. So geometry, and remember, it's not geometry like the full name. It's because your container for geometry is also called geometry, because you could call that anything, right? So because that is default to all new objects in Houdini, it's often the case you're going to use this geometry string. And there you go. So now we are resizing our container to be the size of the bounding box of the particles. Now what we need to do is to also give it a little bit of bounds so that it can portray better the so give it some spacing outside of the bounds. So let's create some lower and upper bounds here. So first I want to use the same values for all these ones. So I'm going to create some connections here. So let's start giving maybe 0.5, I don't know. Let's take a look at that again. Yeah, much better. So it encompasses better the geometry. All right, so now we want to actually input some values in that field, because again, this is, although it's following the geometry, all the values are zeroed out. So we need to actually sample values from the particles and transfer that over to the velocity field. So the way you can do that is by using the gas particle to field here. So the destination field is filament vel. Excuse me. The particles are the geometry, and the attribute you want to transfer is the filament vel, because we have called that in here. So it's also filament vel, right? So let's use that in there. We can see something changing already. Also the mode is copy, so we're going to copy values from the particles onto the voxels, and there you go. Now if you play, you see some stuff going on, not very interesting. So now we need to go to our vector field visualization and change the visualization type. So we want to use streamers, That means we want to see like the vectors themselves, and we have that displayed into a plane, so we're using the XY plane. And also we want to see the distance so that it nicely colors, so that you can see the like the magnitude of the vectors. And there you go. If you take a look, it's going to show us something already. Again, not very interesting because that's showing us just like the like a slice of the whole volume, and also the particles are not moving together with the velocity yet, so we need to actually make the particle follow that like the filament velocity we have sampled, right? So let's try and do that right now. So what we want to do is to and actually I'll create that into another pop wrangle so that we are very so we have very distinct code here. It's easier to follow. So another pop wrangle, and that's, let's call that follow or blend filament vel, okay? Because that's what we are going to do. We're going to blend the filament velocity into the particle velocity. That way we can use other forces in conjunction with the filament, like noises and whatever. So yeah, let's first get this attribute, filament vel. And what I want to do is to actually probably, yeah, let's use that right away. So what you want to do is to blend V. So V will be a lerp for linear interpolation. So we're going to blend the velocity itself, V itself with the filament vel, and how much we want to blend, we're going to define a channel for that. Let's call that blend. And there's another thing I want to do, which is to actually give it a factor for the filament velocity so that you can actually control that. So let's make filament vel, let's do times equals a channel, and let's call that vel factor. All right, let's create the parameters, and there you go. So velocity factor, let's say it is 10, and let's say the blend is 0.8. So we're blending 80% of the velocity into our current velocity, or sorry, of the filament velocity into our current velocity. Now that's going to make our particles move together with the filament velocity, and that's going to start giving us a bit of motion. Still not very interesting because we need to actually start tweaking the values, but you see it's moving. Now one thing you need to pay attention to is that the actual point indices, they make a difference into how that thing is going to work. So if we reverse, use a reverse node, that's going to reverse our polygon. And then if you take a look at the geometry, that's probably going to make it follow a little bit better. So there you go, we have something going on here. Still not cool, but yeah, something is going on there. Now we can start tweaking our parameters here. So let's say the velocity factor is 100. So now you can see something going on here. So you can see some sort of verticals or vortex motion going on here. If you take a look from the top view, we can see that kind of forms a torus or a toroidal force, and that is following our curve. So that's cool, it's starting to happen, right? Yeah, so there you go. Now let's start again doing some stuff here to change these. So if you start tweaking the blend value, so less value will blend less, so have this thing here, not too interesting. If we blend more, you see that trying to follow more of those filaments or the curves. And what I want to do is go one step up and then start changing the filament attributes here. And you see that is basically those two attributes are the only ones we can change for filaments. So the strength is how much it actually follows the curve, and the thickness, or sorry, one very important thing, it needs to be at the primitive level, okay, instead of points. There you go. Now you can see it's trying to follow the curves, and the thickness is not exactly what it looks like. For thickness, first I understand that was like the area around the line, but it's not like that. I think it's more like the fluid thickness. So the less your thickness, the greater your area around the line will be. So you can see like that. If we increase the thickness, so let's say 0.8, so you can see like small curves going on the fluid. So it's starting to look interesting already, right? So it's starting to give us like a nice fluid motion, like an ink, and we can keep it further. So let's go ahead and do some more stuff here. So one thing I want to show you is, now you can see we have our visualization, and we can try and hide our object here, our points, and let's only see what's happening as far as the velocity. So it's giving us a kind of a okay visualization. We can try and change some stuff here. For example, we can try and override the divisions and see a little bit less of those streamers. But what I would like to see is like the whole thing, right? Not only a slice of that. So unfortunately, it looks like the velocity, the vector field visualization node won't give us what we need. So there's no way you cannot use a plane. So I'd like to not use a plane at all and just display like all the voxels and all the streamers for all the voxels. That's not possible. So let's use that in our favor to again learn a bit more about dot networks. So what I'm going to do is to not use this visualization anymore. So we can go back here and let's construct our own custom visualization. So we can do that by using a, so let's do one thing here. Probably let's plug that into another string. So let's merge. And that is because I want to actually control visualization in one side and then the actual particle forces in the other side, because these things can become quite heavy, and once you have tweaked your simulation, it's a good idea to turn that off so you can simulate much faster. Okay, so I'm going to simply split the streams right away. Cool. So what I'm going to do here is probably, let's take a look. Yeah, so let's use a SOP solver. And we are going to use the SOP solver to construct our own visualization. And what we want to do is to give it a name. So by default, the data name is geometry. That means we will be working on this geometry object here. But I want to give it another name because I want to control that separately. I want to turn that on and off on the viewport separately. And let's give that a name, V's geometry, for visualization geometry. And you can see it created a new item here for us. And let's dive inside. So what I want to do is to actually construct something entirely new here. And I will do that by first querying the scalar field we just created. So this filament the vector field. So let's dive inside the solver, and I'm going to use a dot import fields. So we need to give it at least three informations here, which is the dot network, which is the dot node you want to query the fields from, and which is at least one field name. So for dot network and dot node, I'm going to just reference those parameters here because this is already getting a lot of referenced data for us. So this is the dot network and the object mask. So I just want to copy parameter and paste relative references. Same in here. So copy parameter and paste relative references. And I want to import one field, which is the filament val. There you go. So if you middle click, we can see we already have the field imported with the voxels and all the information. Now, what I want to do with that field, now it's just a matter of getting the volume bounds. So let's do volume bounds. So the goal here is to visualize the streamers in the whole voxel data. So we construct the volume bounds. So if you play, you see this box growing with our vector field. Now what I want to do is do points from volume. So let's create a few points, not that many. Let's up the point separation. And then we want to do a velocity, a volume trail, which we can use to actually see the streamers. So the first input is the points, which we want to use to create the trails, and then we need to plug the velocity volumes, which is this. And there you go, velocity volumes. If you only have one, it's going to use that one, or otherwise you can explicitly tell to use this field here. And there you go, now we created our own visualization here, so you can see it's showing the full streamers for all the voxels, and that is really nice. So let's create an output node here, so that it's going to be our output of that vis geometry thing. But you can see it's not showing in there yet. So although we have, yeah, so there you go, now it's showing. And we can also control how many streamers we have in this point separation. Let's do 0.2, and you have more of that stuff. And it's very nice for when you want to just take a look at what your final velocities are, right? But it can become quite heavy, as I told you, so it would be nice to have a way to turn that on and off. And the way to do that is, again, another stuff to learn from .NET. So let's take a look at our spreadsheet in here. It's always good to take a look at this. This is the snapshot of your entire simulation. So you can see we have created a new folder here, new container called vis geometry, which is the type geometry. So it has attributes like you can see here, points, colors, everything we have created inside the subsolver. Okay, so now to like hide or show stuff in the .NET, you can use this node, which is called render parameters volatile. It's a fancy name, but you can use that to display, to turn on, off, display, and render. The way you need to use that is by attaching that data to or attaching that option to some data. And we want to attach that to either the geometry for turning on and off the points. And because right now, if you turn off the point, you still have this thing here. So we want ways to like turn off either one or another, right? So let's visualize that again. And what we want to do is to fetch data. So fetch data will give you access to a specified data inside that object. Okay, so pop object hold a lot of data. Let's fetch its geometry. So geometry, right? So the source data is geometry. The data name you want to use is also geometry. This is basically bypassing that data, but giving you access to the attachments here, right? So we're querying this object here, or this data here, and we can add a render parameters volatile to that one. And if we take a look, and let's play that again, and what we can do now is go to this guy here and turn that on and off. As you can see, you can hide and show objects in the viewport. Same for the streamers. So same thing, create another fetch data, and let's create another render parameters volatile, and the data now is this geometry. Let's use that on both parameters here, and now you can turn that on and off same way, so you can switch both on and off. And just to tighten up things, what I like to do is to transform that into a subnet so it's nice and clean. Let's call that visualization, and what I want to do is to edit parameter interface. Let's dive inside here and let's expose a few parameters. So first, this one, display. So let's call that point or particles, or display particles. Let's also change the type to toggle, which is more UI friendly. Same thing for this one. So let's drag and drop here, call that display streamers, or display filament val. Makes more sense. And that's basically it. Now, sorry, we need to change one thing here, which is to also make this into a toggle. And there you go. Now we can easily switch that on and off for both elements. And is it working? Yeah. Okay, cool. So that's another way you can work with networks and transforming data and attachments. Cool. So now let's make that a bit more optimized. You remember I told you that can consume a bit of time. So what I want to do is to actually drive a enable solver. So enable solver, it's basically an on and off. So it's going to either enable or disable all the upstream nodes here. So once you use the actual toggle here to enable that solver. So let's copy parameter and only enable that when we really want to visualize the thing. So you can see now, let's display the time, the execution time. If we play now, we can see we are at around 15, 16 frames per second. But now if we turn that off, now we are at 24, and that's because I have my real-time toggle checked. If I turn that off, we can go even far, like more than 120 or maybe 60. Yeah, that's cached. But yeah, you can see how much of a difference that can make. So always make sure to have enable solvers and separate your string for visualizers. That can save you quite a bit of time when simulate your final effect. Okay, cool. So that is summing up everything I have for filaments, I guess. So one extra thing I want to do is to actually make that into a bit more interesting stuff. So we want to add a pop wind, so that we add a bit of noise motion to that. Also a bit of upwards velocity, so we can create something like bubbles raising up, which is also cool with that. And you can see it's a very interesting, very fluid like motion, and it's very, very cheap. So let's change a bit the viewport here to have a bit more anti-aliasing and smaller point sizes, because I want to actually, and let's turn off that guide geometry for the moment. So there you go, and you see this thing here is very, very fast. So we're now simulating 5,000 points, which is not much. So let's start increasing that to maybe 100,000 or 10,000. And yeah, still fast, still at 24 frames per second. Like, it's clamped because I'm using let's turn off real time just for reference. And let's do 100,000 points, and you see it's very fast. Well, I mean, it's very fluid like, but it's still very cheap to simulate. And again, let's do 1 more million. You see, it's not bad, right? 4 frames per second, 3 frames per second, but look at how much detail, how much information you have in here, and you can really zoom in to see like all the intricate details. And for example, if we're rendering ink, that really needs a lot of points, which are going to see right after how we can use PDG to generate some seeds for this one, and then get all caches and merge that all together to create like a big point cloud, so that you can really render as points and have a nice softer look to that. But you see, we have simulated already almost 100 frames, and it's like 1,000,000 frames birth rate, which is a lot. So yeah, you can see the filament simulation is very, very fast. Okay, so let's go back to 10,000 just because it's cheaper and it's easier to simulate. And there you go. Now we can see we can probably start taking a look at the other parameters. So now we can really start art directing the thing. So we can look at the blend, filament velocity, and see how much we want to blend. So let's say we want to blend less and give it more like of the pop wing motion, or we can blend 100% and it's going to be like the rolling motion. We can also blend past 1, let's say 2, and it's really following our which is really nice also. I like that. And yeah, there you go. Now let's try and increase the velocity factor, so you can see much more of the vortices going on. That looks very, very cool, right? So let's go midway, maybe 150, and that is very nice. Okay, so now what I want to show you is how you can use a time warp to do some sort of speed ramp on this thing. So let's do a bit more particles, maybe 100,000. And let's yeah, so first thing, I just want to query my pop object from the dot network, just for good measure, because if we had more objects in here, just want to get the pop object from this dot network, so we can do a quick and dirty pop object 1 into the object we want to fetch from this .NET, and we make sure to only fetch that single object. Now what I want to do is a time warp. So time warp will make it easier for us to retime that thing. And what I want to do is evaluation mode set to by frame, because we want to hand animate the frame, and the input range needs to post extend, otherwise it's going to clamp at frame 100. So let's post extend, and I also want to interpolate, because we are going to do a slow motion, and this will better interpolate the motion of the particle. So let's set interpolation to cubic, which is good enough for us to have a smooth movement. And also I want to scale velocities, so it also scales with the slowdown time, right? So let's start creating some keyframes here. So I want to start at frame, let's say 20, I guess. Let's keyframe that. Let's say from 1 to 12, I want to make it into 100 frames. So this is a very fast, yeah, so it's a very fast first frame, like it's starting to, like it's my first frames, those are very fast. And then I want to transition into the slow motion, and what we can do is let's go to our last frame and let's make into, let's stretch, I don't know, maybe 30 frames into that period. So yeah, it's keyframed. Now I want to shift and left click the parameters to open the animation window, and what I want to do is to give that a proper slope to the curve. So let's go without any easy in, and just want to actually easy into the second frame here, so that we can actually get the like slowing down feel. but from here to here I want a straight curve, linear transition. And there you go. Now we can see that working, and then it transitions into a very slow motion, which is playing very fine. And just to see that playing like in real time, I want to drop in a cache node. So let's cache that. What I also want to do is to color my particles by the speed. So let's do a attribute wrangle. So let's color by speed, and I want to do a CD is, so let's cast to a vector. So we're going to create a ramp, but first we need to cast to a vector since it's a color. And now let's create a ramp, and let's call that color profile. And we are going to sample from the length of the velocity, so the speed, right? So let's do that in a separate variable, so that's easier to read. So float speed is length of the velocity. So we want to actually fit that range. So let's fit the speed from a channel. So let's do min and max. Now let's transform that into 0 and 1. Okay, so I think that's all there is to it, and we have one extra parenthesis and wrong, so it's a typo in here. There you go. Now I want to create the parameters. First the colors. I'll start with a dark blue, then going to a light blue, then going to white, and my maximum velocity will be something around 2.1, something like that. Let's also make it background into a darker color, so it's much nicer. Now it's starting to look good, and I think that's it. Now let's cache the viewport and take a look at that when it finishes. Let's actually do that before the time warp. So let's also call that color by speed. And probably need to update those values, and there you go. Now let's cache. So it will take a few seconds for us to be able to see that in real time, but yeah, it's worth waiting a little bit so you can really judge the motion. I'm not going to pause since it's fast, it's almost done. And there you go. So you can see very smooth motion, no popping. The time warp, like the retime node with the cubic interpolation, works good enough for us. Velocities are changing with the retiming also. So yeah, very cool effect. I still think it's a bit too like intense, like the fast to slow is a bit too intense. Probably it's a good idea for us to like go to the pop source, decrease the birth rate, and then do that live. So let's do that live here. Yeah, so probably we want to give it a bit more frames, and then maybe, yeah, maybe that curve a little bit less steep. So and also probably maybe that last keyframe a bit more like less slow motion. So there you go, that's better, I guess. But yeah, now that's all about creativity. So yeah, that's how that's basically the thing I wanted to show you, and it's a very nice, very very fluid like motion with lots of controls for you, and it looks really good already. Alright, so before I finish, I want to show you one last trick, which is to get a few more sources and make that really look like a complete shot. So what I want to do is to use a grid, and let's create a grid with not many divisions, or it doesn't matter really. Let's do 2x2, and we can use a scatter and align if you're on Houdini 18.5, which is a very nice node. And what that will allow us is to change a bit the rotations and have more control. So what I want to do is to copy and copy 2 points. I want to copy those emissions onto those points, and what I want to do is to mount in the grid. So more, yeah, that's right. Okay, so let's go back and switch the height value a bit more. There you go. So it's very noisy now. And what I want to do on the scatter and align is to first open the alignment and blend normal with Y, so that all the emitters are like facing up instead of to the sides, and you can give it a little bit of variation just if you want to. And also what I want to do is rotate around normal. Let's give it a max angle so it has this random direction. And yeah, so let's add a bit more height to this thing here, like so. And we can give it less points, otherwise it's going to be much stuff going on there, something like that. And so yeah, if you can feed that into the DOP network, and what that will do is to create a nice simulation with all those sources. So you can start blending, and all the particles will of course interact, and you can start if you handle with some type of field, it can look very cool. Alright, so that's how you can create a lot of emissions. Of course, you can do that multiple ways. This is a very quick way for you to get this stuff going. Of course, you can vary the sizes and the velocities and all that sort of stuff. But yeah, I'll leave that for you. Okay, cool. So with that, I'm closing, and think that's all for this tutorial. On the next ones, you have access to how we can generate a PDG network to cache a few more seeds and really render that in Redshift with that softer feel that ink requires. So hope you like that one, and see you in the next video. Until that, take care and goodbye.